So when we trained our model, we saw the registration process. And in registration process is where we get the model that we just created, wrap it, and then push it to the model registry. And that model registry is in the MLflow model registry. Now, the wrapping portion of this equation, that's the thing that I want to explain a little bit more and show you the code. And the last session, uh, we saw the model registry. And here in the registering of the model, we saw this section here, which is where we log that model to MLflow. Now, I told you back then on that video, I told you that I was going to talk more about that later. But here you can see line 420. Here you can see how I'm creating an instance of something called model. Now, this model class, that's something that I created. Okay, so if I click there, it's going to take me to the inference.py file that contains the definition of that model. And I want you to notice this is an MLflow PyFunc Python model, which is just a custom model with Python code inside. MLflow supports a bunch of different models. I'm using this one here. And this is a complete definition of what that model is going to do. Now, let's get back just for 1 second and try to understand what's going on here. So remember that during the training process, I'm creating a model using Keras. So let's just go to the model registry here. I have two. I'm going to make this a little bit bigger. Okay. So I have here one version of the model, just right here. Let me actually refresh the page. Yeah, I have two versions. I'm going to go to the version 2 of Penguins. And we already saw the inputs. This is what this model is expecting. It's expecting an island, a Coleman length, a Coleman depth, a flipper length, a body mass, and here is the type that that model is expecting. This is the signature that I created, and a different way of looking at this signature is just by clicking on that specific experiment, going to the artifacts, and I should have here the definition of that model. Here is the signature. This is what the model is expecting. Okay, so a property called island of type string that's required, etc., etc. Now the output of my model expects, or not, doesn't expect, but it's going to spit out a prediction field, which is type string. Remember, this prediction is going to be the species of a penguin, and it's going to spit out the confidence on that prediction, which is just going to be a float number. But if you think about it, the actual model that we built with Keras is nothing like that, because the actual model expects the input layer of that model just expects a vector of numbers. That is why we pre-processed, we transformed the data from the data set before actually providing that data to the model. So if that model expects a vector of numbers and outputs a softmax vector, so another vector with 3 values, how come we are setting a signature that looks like this? Well, the answer is because we don't want to deploy directly the Keras model that we created, the weights and biases, expecting those vectors. We don't want that. We want to wrap that into some Python code that actually expects a JSON file with these characteristics and outputs a proper answer that a human can understand. So that wrapper is just going to get the input, process that input, send it to the model, to the actual weights and biases, to the actual, the Keras model, get the output, and transform that output into this specific format. That's what we want to do. That's the model that we want to deploy out there. And like I mentioned in the previous video, if you try to deploy a model directly, like a neural network directly out there, then you're exposing every single client of that neural network to information that only you should be aware of, like what is the transformation method that I have to use in order to take my raw data that exists, like the penguin body mass in grams, and what is the proper way to standardize the body mass. You're going to have to share that information with every client. And if you make a different decision, now every client will also have to change the way they do that stuff. So you don't want that. You want to concentrate all of that information in a single central location. So every client will send you raw data and will receive the actual species of the penguin without knowing or caring about the internal mechanisms of your model. So that's what's happening here. So now let's take a look at the code so you understand exactly how I'm doing that. Okay, so let's go to so by the way, before we go to the inference, this is where I log the model. Notice that when you're logging the model, you have to provide an instance of the model. So I have to create an instance and provide it to the model. And this is what's happening here. This Python model property is getting an instance of my model, and I'm initializing that model with data capture equals false. We're going to talk about data capturing. You're going to understand what that does. If I go to the MLflow page here, there should be a pickle file, which is this one here. This pickle file is precisely that instance that MLflow is going to get it. It's going to save it, like basically pickle it, and then upload it to the model registry. So anytime I want to deploy this model, MLflow has that instance already created, okay? So you need to keep that in mind. Whenever I'm running my model, that model is going to get initialized exactly the way I save it right here, okay? So I know that model is going to get, by default, is going to be initialized with data capture equals false, okay? All right, so let's take a look at the inference class and how I created this model. So first of all, this documentation here will give you a ton of information. This model implements an inference pipeline. That's usually how we call it, an inference pipeline, or every step that we go through in order to generate an inference or run inference on a sample. So we receive a sample, and we're going to take that sample through a series of steps or through a pipeline just to run inference on it, okay? So this pipeline will have three phases or three components. The pre-processing component, remember, in that pre-processing component, we're going to get the raw penguin data and transform it into the format that my model expects. So basically a vector with, I don't know how many, 9, 11 values inside. After the pre-processing, we're going to go to the prediction step. That's where we actually use the weights and biases of the model to make a prediction. And then we're going to go to the post-processing step. So those are the three steps of my inference pipeline. The model will optionally store the input requests and predictions in a SQLite database. That's important. So I'm building here the ability for this model to optionally save in a SQL database all of the data that goes through that model. And this is very, very important for monitoring the monitoring purposes later. So when we get to monitoring, we're going to see that, well, how do we actually determine how this model is doing? We're going to need the data. And if you're using a service like SageMaker, for example, you don't need to do the automatic storing of the data because SageMaker can do that for you. But if you're deploying this model somewhere else that does not support automatic data capturing, you need to do it yourself. So here I implemented an optional mechanism to save that data, and I'm going to show you the code. Here is a blog post that will give you more information on how to create one of these custom models. You can visit that blog post later if you want. Okay, so here is the constructor. And this is the one that's going to just obviously create an instance for me, and the one that I'm calling at the time of registering the models. So just to create that pickle file that's going to go to the model registry. And there is not a lot going on here. There is obviously some documentation to explain how this is going to work. But basically, I'm doing a couple things, and that is just initializing the data capture property which by default is going to be false. And I'm creating it with false as well. And then I'm also initializing the data collection URI, which by default is just going to be penguins.db. Okay, so if you don't give me a URI to a database, like the name of that SQL database, this is just going to have the value penguins.db. Now, in the future, I'm planning to extend this class to provide support to storing data, let's say in a Postgres database or a MySQL database. So this data collection URI will evolve into more than a file name. But for now, this is just SQLite. So a file name will be provided here. That's what I'm going to use to just create that file. Okay, so nothing else is going here in the constructor. That's it. It's just setting those two properties. Remember, by default, I'm not providing a URI. So that means it's going to be penguins.db. And I'm just saying that data capture is false, which is just the default value here. So yeah, that's how I'm initializing the class. Okay, so there is going to be a load context function. And this is required when you inherit from the Python model context. So the Python model, you need to implement a load context model. So the load context is a function that MLflow will call automatically anytime it initializes a model. So let's say we deploy this model. And the first time that model gets deployed and is going to load, that first time, MLflow will call this load context here, okay? Now, this load context is not going to get called for every single request. We don't want to do that because in load context, we are supposed to add any processes, anything that could take a long time or that we only want to do once, okay? So we want to make sure anything that of that nature goes here, so MLflow knows exactly that it can only load this load context only once, and it doesn't do that multiple times. So here in load context is where we're gonna load the artifacts that we need in order to make this pipeline run. There are 3 artifacts that we need for the inference pipeline. Number 1 is the model itself. That's the Keras model, the weights and biases that we saved, obviously. But remember, also, we need the transformation pipelines or the transformers that we created. Those are the scikit-learn pipelines that we used to pre-process the data. We cannot send a JSON directly to the Keras model. We need to pre-process that JSON object, turn it into vectors that are standardized, that are encoded, etc., and then we take it through the model. In order to do that, we need the transformation pipelines. If you remember, as part of the registration process, when we run the training pipeline, as part of that process, we provided a list of artifacts that were saved in the model registry. Those artifacts are now going to be available to us. Why is that? Because when we ask MLflow to package a model for deployment, MLflow knows to take all of those artifacts and give us those files in a package. So we're going to have access to them. So let's take a look here really quick to the list of artifacts that were registered with this model. And inside this artifacts folder, you're going to see the 3 files that we need. This is the model.keras, weights and biases. This is the features transformer. This is the target transformer. Remember, we use 2 different transformers. One to modify, to pre-process all of the data in the data set, and the second one to just transform the target column. Okay, so these are the 3 that we need. All right, so in the code, in load context, we're going to be receiving a variable that's going to be provided by MLflow that's called context. And context has an attribute inside called artifacts. And we can access our files inside that attribute. Okay, so that is what we are going to be doing here. And I'm going to just skip a few lines here just so I get to that point. Here is where I'm loading those 3 files from my artifacts. So Notice that I'm initializing a features transformer here. And the way I'm doing it is using joblib because I saved these files using joblib. So I'm going to be loading them using joblib. So I'm going to load the artifact name is features transformer. I'm going to load it and I'm going to save it here. And in this one here, the target is doing the same thing. I'm just loading the artifact that's called target transformer. And then the model I'm loading and the artifact is called model. Now, these two names here, if you go to the training and you go to the get model artifacts, here you'll see exactly what those names are. So at the time of saving, of registering the model, I specified those names. I said model is going to be this file that's in this location, features transformer and target transformer. These are the files that you need to save. So here, those files are going to be referenced by that list of artifacts. And that should be here. If I go to the ML model definition, you're going to see the artifacts and you're going to see, hey, features transformer. This is the path of the file. It's artifact/features.joblib. And this is the URI where that file existed before. Notice that this is a temporal directory that I created during registration. So this is not that important at this point. It wouldn't exist anyway. Here's the model and here's the target transformer. So these artifacts, that's the important part, are going to be available to me during the load context function. Okay, and I can load them in memory, initialize them in memory. The next time I get a request, I'm going to have the model and both transformers in memory. I don't have to load them with every request. That's huge. Now I'm doing some other stuff here in this load context. Specifically, I'm checking for the Keras backend environment variable. I'm saying, hey, if that variable does not exist, please set it and set it to JAX. Remember, we did the backend of our model. When we generated our model, we used JAX. I want to make sure that at this point, JAX is the backend that I'm going to be using. So I'm setting that environment variable if it doesn't exist. Then I import Keras. Then I configure the logging mechanism. By the way, I have not talked about logging. I'm going to probably talk about logging later. This is just a function. I'm going to just go over it like really, really quick. This is just a function that takes care of configuring the Python logging library. So when I'm printing out stuff, I know exactly what the format is and what exactly I want to print. And the configure logging function, first, it tries to load the file that's called login.conf, and it's going to use that file as the configuration. And if it doesn't find that file, it's just going to use a basic configuration with this format, okay? And I provided that file, so you're going to see it here. And this is what controls the logs that go to the console. If I get to deploy this model, let's say if I deploy this model somewhere, I can include that login.conf if I wanted to in order to modify how the logs are going to look, okay? So that's what's happening in this configure login here. I'm going to do that whenever I load the context. Let's go back up. Then I just print out a message saying, hey, loading model context. Then here, I'm just going to be loading another environment variable. So here's the thing. I added support because this model, I want you to remember this model, at the time of creation, I can provide a collection URI at the time of creating the model. That's during training. Sometimes, however, you might want, after that model was deployed, you might want to change that. But the only way I support doing that is through this collection URI, it might be harder for me to change that down the line because it was already set. So one way that you could use, that I'm using here, there are multiple ways to do that, but one way that you could do is support changing that value through an environment variable. And that's what I'm doing here. If that environment variable exists, I'm going to set the data collection URI to whatever value that environment variable has. So even if I initialized this with the value penguins.db, I can later change that on whenever I deploy that model. I can set an environment variable, set it to database.db, for example, and that will override, that will take precedence over whatever initialization I used when I created the model. So that is what's happening here. At this point, I'm loading just that environment variable and setting it to data collection URI. Then I print out a couple of messages to the screen, and then I go into loading the picture. So that is what's happening inside the load context. Again, this is only going to run once whenever that model gets loaded. So now we have to go into the actual execution of the pipeline. And MLflow gives us access to one function that we need to implement that's called predict. This is the function that MLflow is going to call for every single request. Every time we send a sample to our model, MLflow is going to call the predict function. And the predict function receives context, receives the model input, which is what we care about. That's the model input, that's the data. And it supports a list of parameters as well. So we can make a request and specify parameters that are going to be modifying that request somehow. We're going to talk about how I'm using that in a second. So this function will handle the request received from the client. The client is the one that's sending a request. This method is responsible for processing the input data received from the client, making a prediction using the model, and returning a readable response to the client. So basically, this predict, whatever it comes out of this predict, that is the answer that the client will be getting, okay? The caller can specify whether we should capture the input request and prediction by using the data capture parameter when making a request. Now, remember, we initialized this class with a data capture property. But this data capture property is like the general way to initialize that model. But I can later send that or change that per request. So by default, the model might not save any information. But for one specific request, I might want to just, yes, please, for that particular request, I want you to capture it. And I can send a parameter with that request that says data capture equals true. And that particular request will change, will be captured, which is great. That gives me a little bit of flexibility. Okay, so let's see what I did here inside. So first of all, this predict function is going to support different formats, okay? And I'm just making sure at this point that I can process both formats. So as you can see here, I'm saying if the model input is either a list or a dictionary, then load it in a data frame, okay? If I pass here a data frame, I don't have to do anything. I can call this method with a data frame directly. I don't have to do this. But if it's a list or a dictionary, meaning a dictionary will be like a JSON file, I'm going to turn it automatically into a data frame. So from here now, I can just work with model input. I don't have to be, filling out my code with conditions. If it's a JSON, do this. If it's that thing, do that. I just do it one time and I do everything here. So I'm going to log out how many samples are going to be, or we received. So we're going to get something that says receive prediction request with 27 samples or one sample. That's what I'm logging out here. Then I'm going to initialize the model output here. The output is an array because remember, this predict function can receive one sample or a batch of samples, which is great because you don't have to send one request at a time. You could be sending multiple requests at a time. And then I'm going to go into the pipeline. So let's see step by step what's happening here. First, I'm going to be calling process input, okay? And this is a function I created that receives the model input, and it's going to process that model input and save it into a variable that's called transform payload. And obviously, you don't have to have a college degree to understand that this transform payload is basically the original data, applying to it the transformation pipeline, and the result is what's going to come in here. So let's go to process input, and let's make sure that's exactly what's happening. So this process input is going to process the input data received from the client. This method is responsible for transforming the input data received from the client into a format that can be used by the model. Yeah, and how are we going to do that? We're just going to take the features transformer that we loaded as part of the load context, and we're going to just call the transform function to transform the payload. And as a reminder, for those of you who are not used to this, if we go to, I'm going to the transformation, the transform step here of the training pipeline. Remember, that's exactly what we did. Well, in this case, it's a fit transform. Let me just find the transform fold. Whenever we wanted to do that, we just call the transform function. I encourage you, I'm not gonna go through the same explanation again, but I encourage you, in the previous video, the one that talks about the training pipeline, I spent quite a bit of time explaining why you call transform and not fit transform. You only do fit transform on training data, and from there on out, on test data, on production data, you always use transform. The explanation is in the previous video, and it's one of the keys that you need to get out of this class, okay? So anyway, here I'm just transforming all of the features that I received, and I'm going to return that out. There is an exception handling here just in case there is something that's wrong with the payload. I'm just going to return none. In that case, if I couldn't run this transformation, I'm just going to return none. So let's go back out. We're back here. If transform payload is not none, meaning I was able to transform everything, then I'm just going to print out a log, and then I'm going to call self.model.predict. Remember, this self.model, this is our Keras model. And what am I going to be passing to the predict function? The transform payload. This transform payload is a matrix of it's a vector of vectors, or a matrix, where every single row is just going to be a vector with the information of one sample, right? If I pass 3 samples, I'm going to have a matrix with 3 rows, or a vector with three vectors inside, okay? Okay, so I'm going to run the predict. I'm going to get the predictions right here. These predictions, each of those predictions is a softmax vector. So there are going to be 3 values on each one of those predictions. I don't want to just return vectors outside. I want to interpret that softmax vector and determine which is the correct class. That's the one that's winning here, the one that's more likely. So return the class and return the confidence, basically the value of the softmax that's the highest. So in order to do that, I'm going to call the process output. Okay, so let's go to the process output. The process output, this method is responsible for transforming the prediction received from the model into a readable format that will be returned to the client. So whatever comes out of process output, that's the information that goes to the client. Okay? All right, so how do we do this? Well, I'm creating a result array here, and I'm just making sure that output that I received is not none, because, if I couldn't do the transformation before, or the model made an error, I might get a none value here. And then I'm saying, okay, so the prediction is just the argmax of the output. Remember, the argmax property is just going to find the maximum value on that array of 3 positions, and then it's going to return the index of that maximum value. So let's say I have 0.2, 0.8, and 0.1. Well, you can have that. 0.1, 0.8, and 0.1. The maximum value is 0.8 and it's in position 1. So 0, 1. That's the value that I'm going to return, 1. So this is giving me now prediction. Now it has the index of the class that's the most likely, the answer, the species that's the most likely. And confidence is just giving me the max value. So the 0.8. That's going to be the confidence that I'm going to return. So now I don't want to return the prediction as just a number. I want to return the actual class. So how do I access the actual classes? Adelie, Gentoo, Chinstrap. Well, I have the target transformer as one of the assets that I loaded during the load context. And I can take this target transformer and access internally. I can go inside, access the species column transformer that's saved here, and get the list of categories. Okay, so these are the list of classes, and then it's as simple as just using this array of classes with the prediction index to just return the corresponding class for that index. So if the prediction is 1, I want to return, I don't know, whatever number 1 is, might be chinstrap. I don't even know what number 1 is. And remember, because I'm working here with vectors, because the output here might not be just one answer for one sample. If I send a batch of samples, I'm going to get here a batch of responses. I'm working with vectors. So that's why I'm doing like the vectorization here, just so I can actually return, do this in a single line, return all of the classes for a single value. Okay, so after doing this, now here at this point, now prediction is not an index anymore or a vector of indices. It's just a vector with the actual classes. So I can just return the actual results that I want to send back. And that is, I'm just going to go through the union, the zipping of predictions and confidence. So that's going to be, imagine that you have like 2 arrays and you're putting them together, okay? And now I can go and take 1 prediction and 1 confidence, the second prediction, the second confidence, and I'm going to be just building like a JSON here that I'm going to return back. So that JSON is going to have the prediction, and the confidence is going to be the confidence that comes here. These values are NumPy values. So everything here that I'm working on with here, this vectorized, all of this creates NumPy values. You got to be sure to extract the dot item from the value, because so it can be serialized. So the answer of this process output is going to be sent back through the wire to a client. This might be stored, like this might be running in, let's say, AWS or Google, a server somewhere. You want to send that over the wire. So that means that the answer of the model is going to be serialized to send over the wire in JSON format. You cannot serialize a NumPy value. So just make sure, that's why I'm doing the dot item here. So I extract the actual float value or string value, and that can be serialized. So anyway, the output of this process output now is going to be an array of JSON objects, okay? Where each JSON object is going to have prediction and confidence inside. Okay, cool. So if I go back to the initial function, the predict function, in this portion here that we just saw, this is the portion, these 3, 4, 5 lines is what executes the whole pipeline. We started by processing the input, then we call the model predict, then finally we process the output. So this is everything we need. Now, I want to do something else before returning model output. By the way, I already have the output that I want to send back, but remember we wanted to implement optional data capturing. So that's what's going to happen right here, and then we're done. So this condition here, which you can parse on your own, I'm going to explain high level what it does. What this condition does is checking whether data capture is enabled or not. We have 2 data captures here. We have one that's global and one that's specific for this function. And this super huge condition is just making sure the closest one to this code is the one taking precedence. Meaning, if I say true above, so at the class level, data capture is true, but I specify false for this function, it should not capture the data. If I said at the global level that is false, but I said true at the function level, it should capture the data. As a fun challenge, if any of you can come up with a more elegant way of writing this condition, please let me know, and I'm happy to just discuss it and change it here. But anyway, this works. This does what I want. If data capture is enabled, I'm going to go and call the self.capture data, self.capture function. So this self.capture function, let's see what it does, because it's kind of important. So first of all, it's going to receive the input and the output. okay? Because I want to lock both. I want to have a database that says, here is the sample that I received. Here is the prediction that I created, okay? So this method will save the input request and the output prediction to a SQLite database. If the database does not exist, this function will create it first. So if there is no SQL database, it will automatically create the database. By the way, working with SQLite is just a blast. It's so simple to do, especially if you're working in Python. And it's just so many problems you don't have to worry about. It's just amazing. So what's going to happen here, I have a try catch here, or try except in the case of Python, just making sure there is no errors. So I'm going to create a connection, okay? And the connection is going to receive the name of the database, okay? By default, this connect object is going to create that database if it doesn't exist, okay? I don't even have to worry about that. So I'm going to create a copy of the input. So I'm getting the data frame. I'm just creating a copy of it in the data frame. I now have a new data frame that's called data with all of the values that came in the input. I'm going to add a new column to every one of those values, and that column is going to have the date time of right now. So I'm just adding a timestamp to that column. Why is that column for? Well, I want to take a look at the database and understand when a specific sample was captured. So I need that date. So that's what I'm doing. I'm adding the date throughout all of the samples that in this data place. I'm adding two more properties. One is the prediction, just what was the prediction that the model make. And for now, I'm just initializing that with known. I'm going to add a value later. And I'm adding the confidence as well. For now, this is going to be none throughout all of the rows. I'm going to add a value later. And then I'm adding another property, okay? And this property is called species. And this property is going to be the ground truth. I should have called it ground truth. I don't know why I called it species, but I should have called it ground truth. This property is going to be the ground truth. Now, hold on your horses. This is in production. This model is running in production, received some data, created, generated predictions for that data, saving that in the database. So what is the ground truth of one specific sample? Well, we don't know here. This is the property that will have to be filled out by a labeling team. So whenever we want to make sure that the model is making good predictions, we need a labeling team, somebody that's going to come and generate a ground truth value for this sample. So in this case, that property is going to be called species. We're going to talk a lot more about that property when we get in a couple sessions when we take a look at the monitoring pipeline. So anyway, it's going to be none for now, and that's the way it's going to be saved. Now here, I'm just going to fill out the prediction and the confident properties, okay? So how am I going to do that? It's just very simple. If I have an output, so if I was able to produce an output for this model input, I'm just going to do a for loop through all of the outputs, grabbing the prediction and storing that prediction right here, and do the same thing with confidence. So at the end of this line here, now my data frame contains all of the original columns from the input, plus the predictions, plus the confidences, plus a date, plus a species column that's going to be null. And that null is because I don't have a value at this point. A labeling team will have to create that later. And then let's add one more column, which is going to be like a random GID or GUID, which is just a global unique identifier to just represent that column. This is important because later on, whenever we're labeling data, we want to match the ID of a sample with the ID of a label. Those IDs are going to come in handy. So I'm just adding that ID so we have a unique representation in the database of every single sample. Nothing fancy. This is just a random ID at this point. After I do that, I have all of the data that I need at this point. After I do that, I just need to save all of this to the database. And you can do that very easily the data frame pandas supports doing this very easily. You call the toSQL, how you name it, the name of the connection, if it exists, just please append all of this data and don't add an index to, like a data frame is going to have an index column 0, 1, 2, 3, 4, 5. Please don't add that index. And that's about it. So after I execute this capture function, all of the new data is going to be saved here in a Penguins file. So that is how our custom model works. So as a reminder, whenever I run my training pipeline, the last step is going to register my model. If I can go here, it's going to register my model. And the model that I'm registering in the MLflow model registry is a custom instance created using this class here. That's why during the registration process, I pass this instance, and I also specify the code that MLflow is going to need in order to actually run this instance. So see this code path? The code path is pointing to the inference.py file because it's needed if we want to give MLflow access to this, okay? Now, in the next video, we're gonna see how we deploy this model locally. So I'll catch you there.